Hi, I'm Wang from George Mason University. It's my pleasure to present our paper, GraphSPD, Graph-Based Security Patch Detection with Enriched Code Semantics. This work is done by Wang, Xinda Wang, Sun, Sushil, Jajodia, Haining Wang, and Li. As we know, security patches are critical for software maintenance since their code changes used to fix some security vulnerabilities. However, from our observation, we find a large volume of open-source security patches are silently released without reported to National Vulnerability Database, the NVD, or provide any explicit descriptions. For example, they did not provide their security impacts in their change logs. So attackers might carefully inspect the source code changes and leverage the hidden security patches to launch end-day attacks against the unpatched downstream software. So users need to timely detect and apply these security patches before being exploited. To detect these hidden security patches, usually only the source code changes are available since not all patches have well-maintained documents. However, for existing solutions, they regard the source code as a sequences and apply sequential-based solution. So it will lose the structured information in source code, for example, the control flow relationship. In our work, we propose a new solution called GraphSPD that is a graph-based security patch detection system. In our work, we first propose a new graph representation for patches called PatchCPG. It includes both the syntax and the semantics information for patches, including the abstract syntax tree, control dependency graph, and data dependency graph. The PatchCPG also includes the version information from the pre-patch source code and the post-patch source code. Then we design a patch-tailored graph neural network model called PatchGNN to capture the diverse patch structure information with a multi-head attention mechanism. So from the first step, we need to convert a patch into a graph representation, PatchCPG. In our solution, given a patch, we first roll back the project to retrieve the pre-patch source code and the post-patch source code. But we only retain the files and functions that are directly related to the source code changes and use YARN to generate the code property graphs for the related functions of both versions. After we get the pre-patch CPG and the post-patch CPG, we will merge these two CPGs into a patch CPG. And the merging principle is that we will merge the identical context statement and retain the added and deleted statement in a unified graph. Then we can get the patch code property graph, short for PatchCPG. It is a unified graph that encodes rich patch structure information. The PatchCPG includes the version information for nodes and the edges to indicate which statements are added, deleted, or context statement. We also include 3 different relationships in PatchCPG, including the control dependency relationship to indicate which statement decides the safe or unsafe operations, and data dependency relationship to indicate where the value comes from, and of course, the abstract syntax tree to show how each statement looks like. But after getting the PatchCPG, we face a small issue, and that is the PatchCPG is too large and contains much noisy information from its context. So in our solution, we also perform code slicing to reduce the graph size and to generalize the model capability. So in our work, the slicing principle would be for the context in the PatchCPG, we only retain the context statement that are directly connected to the added and deleted nodes in the PatchCPG. Then we design a patch-tailored graph neural network model called PatchGNN to identify the security patches. And the challenge is how to embed the PatchCPG and convert a graph into a numeric format, and how to handle different relationships in PatchCPG and learn multiple attributes. And in our model, we first convert the graph structure into a adjacency matrix and embed nodes into 20-dimensional vulnerability features, including code snippet metadata, identify and literal features, control flow features, operator features, and API features. We also embed edges into 5-dimensional binary vectors. In the binary vector, the first 2 bits indicate if this edge appears in pre-patch CPG or post-patch CPG. And the last 3 bits indicate the relationship in the edge, including the control dependency, data dependency, or abstract syntax tree. The reason we embed edges into a binary vector is that we will use the edge embedding as a key for a multi-head attention mechanism of our graph convolutional layer. So here, each dimension of the edge embedding presents a relationship, and the value can only be 1 or 0 because they are from a binary vector. That means they can indicate the on and off of the edge. So with multi-head attention mechanism, we can perform graph convolution over 5 different subgraphs with different convolutional weights. So that means our convolution are conducted over 5 different channels, and then we aggregate all the information to the nested layer. We implement our GraphSPD in Scala and Python on top of Yang and PyTorch, and evaluate the performance of GraphSPD with 2 datasets. The first dataset is called PatchDB. It is built up by ourselves. It is released in NDSS 2021, which contains 12,000 security patches from over 300 GitHub repositories. And the second dataset is called SPIDB, which contains 10,000 security patches from FFmpeg and the Chemo. In our evaluation, we compare the GraphSPD with sequential-based solution and the vulnerability detection method. We also did a case study on 4 different open source repositories to show the model generalization ability. For the sequential-based secure patch detection, like PatchRN or SPI models, they use a twin RN structure to identify the security patches. So in our comparison experiment, we can find the GraphSPD can achieve the accuracy of 80% and the F1 score of 0.56. And compared with the twin RN scheme, the accuracy can increase by 10% points, and F1 score can increase by 0.1. And we also find the GraphSPD is more efficient since it can increase precision by 28% and decrease the false positive rate by 14%. Then we compare the GraphSPD with 5 different vulnerability detection methods. For a vulnerability detection method, a patch is identified as security patch only if there are vulnerabilities detected in their pre-patch source code and no vulnerability detected in their post-patch source code. And in our experiment, from the result, we can find the GraphSPD can detect 14.4% of the test security patches, and the detection rate is 2.5 times that of the best vulnerability detection method. Finally, we also did a case study on 4 open source repositories, including NGX, Xine, OpenSSL, and ImageMagick. For example, in NGX, we select 4 consecutive versions and totally find 787 commits. But after screening, only 486 are valid commits. And we perform GraphSPD and totally detect 27 secure patches from them. But after the manually verification, 21 of them are real security patches, so the precision is about 78%. We also did the same case study on Xine, OpenSSL, and ImageMagick. And from these 4 open source repositories, we totally find 88 security patches, that is hidden security patches. And these hidden security patches might be threat to software security since attackers might leverage the hidden vulnerability in these hidden security patches to launch end-day attacks against the unpatched downstream software. And in our work, we propose GraphSPD, which can present patches into a graph representation called PatchCPG, and identify security patches with a graph learning model, patch GNN. And it can achieve higher accuracy and few false alarms compared with the sequential-based solution and the vulnerability detection method. And in our work, we currently focus on C and C++ language. So in our future, we will extend the GraphSPD into other programming languages like Python, Java, and even binary code. And that brings us to the end. I would like to say thank you for your time and attention here. If anyone have any questions, I'm happy to open up a discussion here, or you can contact us through these emails.
Great work. I'm Shitong from Meta. So my question is, seems like the final outcome of your model is whether this patch is patching security issues or not. So my question is, did you run or try any sort of more baseline analysis, for example, possibly using some NLP technologies to directly try to identify this attribute of the patch by, for example, just the title or the commitment message of the patch without even looking into the code itself?
That's a good question. So from our observation, we find a larger security patches do not have like the well-maintained subject or the commit message. And of course, commit message are an important part in the for the commit or the security patches, but not all security patches have the well-maintained documents because it depends on the habit of the software developer or the maintenance policy for different companies or software vendors.
I see. Can I have a second question?
Yeah. Oh, please.
So then from your evaluation section, it seems like the precision for some of the OSS data sets are around, let's say, 50% or so. So did you run analysis for the failed cases? What were the main reasons behind those?
You mean recall or the false negative rate?
So if the precision is like 50%, that means like 50% of other cases you didn't identify correctly. Is that right?
Yeah, for the precision, that means, for example, if we detected 100 security patches, only 50 of them are real security patches.
Right. So yeah, I'm talking about the false positive then.
Yeah. So for the false positive, they manually it's mainly lying in the non-security patches, but they have very similar patterns with the security patches. For example, they use if statement to decide some critical operations in the source code. And that could be a critical pattern for security patches, but for some non-security patches, they also have these similar patterns. So they will be detected in this model and generates the false positive.
Okay, got it. Thank you.
Hi, I'm sorry if I missed and if you already mentioned. I have a question about how did you identify the vulnerabilities for hidden security patches? Because you said you identify a vulnerability if it exists before the patch, but it doesn't after the patch. But if it's hidden, how did you verify there is a vulnerability before and after? There's no vulnerability after the patch. And my second question is, when you also showed that you compare you extract the program slices before patch and after the patch, and how does it impact you if that patch scattered around multiple functions, and or how many lines of code changes, how impact that your analysis?
So for the first question, I think your question is in our evaluation for compare with the vulnerability detection method, right? Mm-hmm. Yeah, for the vulnerability detection method, a patch is identified as secure patch only if there are vulnerability detected in pre-patch source code. So we run the vulnerability detection and see if there is a vulnerability detected in the pre-patch source code, and also run the same test on the post-patch source code and to see if this vulnerability has been fixed.
Okay, thanks for the clarification. What about the second question? Like, does your tool impacted by the how many lines of code changed in one commit, or like sometimes some security patches scattered around multiple pages or multiple functions? So, like, how does your program slices impacted by those large commits or multiple functions changed?
Yeah, for the second question, so indeed there are a little proportion of the security patches can multiply multiple functions, but if the software developer multiply multiple functions, there will some marks in the patches, right? And then after we return the files and functions from the source code repositories, we can get several functions. And after we generate the code property graph, it might be multiple graphs in the patch CPG, but it will not affect our identify and forwarding processing.
Yeah, I ask this because since we are talking about open source tools, and developers might tend to inject, non-security related patches in the same commits. So how did you separate those non-security related changes and security changes in the same commit?
Oh, yeah. So that is another question. That is called a multi-patch, like a patch to generate multiple functions, for example, including the security changes and non-security changes, right? So in our current work, we did not consider that situation, but we will extend this work in our future work. And in the data sets that we use, we have manually verified that for the samples, each samples only fix a single vulnerability and did not have other functionality like add new features or fix functional bugs like that.
Okay, thanks for the clarification.
Right, let's thank the speaker one more time.